next video, we're going to look at Le Chatelier's principle. Le Chatelier's principle is really just a way of explaining how a system at equilibrium is going to respond to a stress. And a stress is something that's essentially going to temporarily knock the system out of equilibrium. So if you change a temperature, if you change a concentration, if you change the pressure or volume on a gas reaction, all of these things can temporarily knock a reaction out of equilibrium. Rather than the rates of forward and reverse reactions being equal, the reaction will either shift to the right and the forward reaction would increase, or the reaction might shift to the left and the reverse reaction would increase to counteract the stress. So the system is going to shift in a direction to reduce or counteract the stress in an attempt to return to equilibrium. That's the goal. And eventually, the system will kind of neutralize this or counteract this stress, and the system can return to equilibrium. And again, just remember the conditions to return to equilibrium. You have to have a closed system, has to be a reversible reaction, so on and so forth. So what we're going to do is we're going to figure out which way the reaction shifts first based on a stress. So we're going to figure out if the reaction shifts to the right, meaning the forward reaction rate would increase, or if it's going to shift to the left, meaning the reverse reaction would go faster than the forward. And then based on this, we can always figure out what happens to concentrations of reactants and products, because whatever I point to is going to be made and go up, and what I point away from is going to go down and get used up over time. So for instance, let's say I have this reaction here. A plus B goes to C plus D, and originally it's at equilibrium, so we'll put these double arrows. And let's say there's a stress, and we figure out because of that stress, the reaction shifts to the right. Now, first of all, what does that mean? That would mean that these rates of forward and reverse reaction are now no longer equal. The reaction is really majority is going to be going to the right. Essentially, the forward reaction rate is going to be much greater than the reverse reaction rate. If this is the case, what's going to be happening to A and B over time? Well, A and B are now the reactants getting used up and going to the right, so they would be going down over time. C and D, what I point to, is being made, so that would go up over time. So if you're ever asked about what's happening to concentrations, first figure out the shift, whether it's going to the right or to the left. Okay, let's say same reaction, but instead we figure out the shift is to the left, meaning that the reverse reaction is now going faster than the forward. So if this is the case, what's happening to C and D over time? They're being used up, so those concentrations would go down. A and B, what I'm pointing to, is being made, so those concentrations would go up. So again, figure out what's going on with the shift of right or left, and then from there you can figure out what I point to goes up, what I point away from goes down. So let's start talking about some of these stresses. So one stress is changing the concentration of one of my reactants or products. So if one of the concentrations goes up, and how could it go up suddenly? So let's say I add something into the system. I increase the amount of reactant or product that's present. What's going to happen is this is going to shift my system out of equilibrium. It's going to shift away from the thing that's added. It wants to use up this excess. So what you're going to see in this using Le Chatelier's principle is I have a little mnemonic device that I like to use. And let me just show. Okay, so here's my mnemonic device that I like to use. I like to say, and this is not something that you should write on like a test, because if it's a grader other than me, they're not going to know what you're talking about. M-A-L-T. And this stands malt. It stands for if you have more of something, it's going to shift away from that thing, the reaction, which makes sense. If I add too much product into my system, okay, the system wants to use up that excess product I just put in, and it's going to shift away from that side in an attempt to bring down that species. If I have less of something or too little of something, it's going to shift towards that particular product or reactant to make more of it, to fill it back up. So more goes away, less toward. More away, less toward. And you can really use this to figure out almost any shift that's going to happen in the reaction in response to a stress. When we get to pressure volume changes, it's going to be slightly different, but this works for any change in concentration and will eventually work for any change in temperature too, with a little tweaking. So let's look at an example here. So let's say I have this reaction. Here's my reactants, here's my products, and I say, hey, a stress happens. All of a sudden, I'm going to introduce more CH4 into the system. What's going to happen? So if I increase CH4, find which side of the reaction it's on. Here it is on the left-hand side. So if I have more of it, what's going to happen? More away, less toward, malt, right? So if I have more of it, it's going to shift the reaction to the right. Equilibrium is going to shift to the right because it makes sense that the reaction should use up this extra CH4 so that it could return to equilibrium, so that it could eventually bring that concentration down over time and restore the equilibrium constant. So equilibrium is going to shift to the right to use up the added CH4. What does this mean, shifting to the right? It means the forward reaction rate increases. Okay, the forward reaction is occurring now much faster than the reverse reaction, so it's no longer at equilibrium, but it's doing this in order to return to equilibrium. If I'm shifted to the right, what's going to happen to the concentrations of these reactants? I'm pointing away from them. They're going to get used up. So the H2O and the CH4 are going to go down over time. And that's going to be counteracting the stress. The stress of having added more CH4. By shifting to the right, I can now use up that excess, and the reaction can get restored to equilibrium. Because if I've increased CH4, I don't have the correct equilibrium ratios anymore to equal the KEQ for that reaction. We'll see that in a moment. Okay, and then if I'm shifted to the right, what's happening to products? Those are going to go up over time. So that's why the reaction has shifted to the right, to counteract this stress. More away, less toward. Okay, if the concentration goes down, so more away, that's part of malt that we said so far. Let's look at the second half, less toward. If the concentration goes down, the equilibrium is going to shift toward that substance to make more of it. It makes sense. It's counteracting the stress. If I have more of something, it needs to shift away from it to use it up. If I have too little of something, less of something, it wants to shift toward it to make it. So let's say same reaction, but my stress is now CH4. I've decreased the concentration of CH4. How has that happened? Maybe I remove it from the system once it's been, or I have less of a. How does that happen? Maybe I remove it from the system. Maybe I've added something and that reacts with it. Different ways that this stress could have been made. But I'm telling you the stress is that I now have less CH4 in the system. What's going to happen? So if I have less CH4, less goes toward, right? The reaction is going to shift to the left, essentially to make more of it, to fill it back up, to counteract this stress. So the equilibrium will shift to the left. What does that mean if it shifts to the left? That means the reverse rate, the reverse reaction is now going at a much faster rate than the forward. And this is going to do so in order to reestablish equilibrium. In order to reestablish equilibrium, what's going to be happening if I'm shifting to the left? That means that my products are going to now be used up. So the H2 and CO would go down over time, and that makes sense that these reactants would be going up over time. And that makes sense because it's counteracting this stress on the CH4, which was that it was too little. I need to fill it back up, and to fill it back up, I need to have shifted to the left. So more away, less toward malt. Again, don't write malt anywhere on a free response and an explanation. Just explain it in your own words. Okay, let's talk about the reason. So again, here's just a general reaction. A plus 2B goes to C and plus D. Take a moment, write the KC expression. So the KC expression is the products in their in square brackets to represent molarity, raised to the power that is the coefficient over the reactants, raised to the power that is the coefficient. Make sure there's no plus signs in between. They are products on top and bottom. So let's say my stress is that there's a decrease in the concentration of C. Okay, that's my stress, a change in concentration. So if C goes down, let's talk about what's going to happen to all these other concentrations. What do we know about Kc for a reaction? Kc is a constant as long as the temperature is not changing, because we said temperature can change Kc. K is constant. In order to be at equilibrium, I need this set ratio, C times D over AB squared, has to be constant. If it's not constant, then if it's not this right value, then I'm not at equilibrium. right? To be at equilibrium, I need Kc to be constant. So if C goes down, in order for this to return to equilibrium and Kc to be the same, let's talk about what has to happen to these other concentrations. Okay, well, D would have to go up, right? So if C's going down, D would have to go up to counteract that. And what would A and B have to do? They would have to go down, because I would want these numbers in the denominator to be smaller so that I'm dividing by a smaller number and I can eventually bring this, fraction back up higher. So once I've introduced this change, it does change my, my concentration of C, and to counteract that, as I said, these other concentrations are going to change. In order to bring D higher, in order to bring A and B lower, the reaction would have to shift toward the right. It would have to shift in direction to make more D, to bring that up. It would have to shift to the right to use up A and B and bring those down. So it makes sense when you're looking at it from an equilibrium constant expression standpoint. Okay. Question: if a substance that's not involved in the reaction is added, would that shift the equilibrium? Nope, it's not in the equilibrium expression. So if I go back into this kind of explanation based on the equilibrium constant expression, if I had some other element E and I added it to the system, that's not changing my concentrations of anything involved in my equilibrium expression and anything involved in this reaction here. So it's not going to make a difference. If it's not a substance that's in my equilibrium expression, it's not going to have any effect on shifting the reaction. The reaction can remain at equilibrium and it will not shift. Okay? Here's another question. What if one of the substances are a pure solid or pure liquid? Adding or removing it, would that shift the equilibrium? So let's take a look. So let's say here's a reaction that goes with a KSP. This is a KSP reaction because I have a solid and it's dissolving into its aqueous ions. It's at equilibrium, double arrows. Here's my Kc expression. Notice the solid's not in it. What if I added more solid AgCl? Would that shift the reaction? And the answer is nope. It would have no effect. Why? Because it's not in the equilibrium expression. Even if I were to add or remove some AgCl solid, its density or concentration would stay the same, and it's not going to shift the reaction. If I take some away, it still has the same concentration. Say it still has the same, number of moles per liter. It's just has less mass, maybe. So if I add or remove a pure solid or liquid, even if it's in the reaction, it has no effect. Why? Because it's not in my equilibrium constant expression. My Ag plus would still stay the same. My Cl minus concentration would still stay the same. So I'd still have the same Kc. Still be the same. Still do the same, no shift. Okay, take a moment, try this example, and then check your work. So if I were to, in this column, we're telling which way the reaction shifts, to the right or the left. In this column, tell me based on this shift, what's happening to the concentration of H2. So if I were to shift, if I were to increase N2, more goes away, more N2 would shift to the right. And if I shift to the right, I'm pointing away from H2, so H2 would go down over time, it's being used up. If I were to add NH3, okay, here's NH3 on the right, adding it, I have more of it, so it would shift away, it would shift to the left, and now I'm pointing to H2, so it would go up. If I were to decrease N2, here's N2. If I have more away, less toward. So if I have less N2, it's going to go toward it, so it would shift to the left, and I'm pointing to N2, so it would go, or I'm pointing to H2, so it would go up. It's being made. If I were to remove NH3, then removing that would have less of it, right? Less goes toward, it would shift to the right to fill it back up, and I'm pointing away from H2, so it would now go down. If I add any gas is not in this reaction at all, so it would have absolutely no effect on shifting the reaction. It would have no effect on the concentration of H2. It would remain the same. I'm still at equilibrium. Okay, let's just talk about temperature as another stress. So remember, if a reaction's endothermic, okay, heat's absorbed. If it's exothermic, heat is released. If it's endothermic, delta H will be positive. If it's exothermic, delta H would be negative. This is all review from the thermochemistry chapter. And if something's endothermic, or I see it, delta H is positive, I can actually put heat into my reaction to create a thermochemical equation, and I would put heat on the left-hand side, or the reactant side, because it's getting used up or absorbed in the reaction. If I have an exothermic reaction, I could put heat into my equation by putting it on the right-hand side, or the product side, because it's being released or made as the reaction goes on. So for example, here's my first reaction, and I'm telling you here's the delta H. Put heat into your reaction. So delta H is positive, it's endothermic. So I can put the word heat on the left-hand side. I can actually put 182.6 kilojoules on the left-hand side. But this value of heat, or the word heat, on the left-hand side to show that heat is absorbed in the process, it's a reactant. In the second one, okay, it's exothermic because delta H is negative, so I can put heat as a product on the right-hand side. Notice that I'm not putting minus heat anywhere. I'm always putting a positive. It's just the side of the reaction tells me whether it's endo or exothermic. And if I wanted to, instead of the word heat, I could put 483.6 kilojoules on the right-hand side instead. And I wouldn't put that as a negative. The sign of the reaction is just showing me whether heat's absorbed or released. So if I put plus 483.6 kilojoules on the side, it's telling me that's getting released. Remember, the sign here is just telling me direction. Okay, now that we know this, any change in temperature, we can actually look at heat instead. So what's going to happen is an increase in temperature is going to favor an endothermic reaction, since endothermic reactions absorb heat, and a decrease in temperature is going to favor an exothermic reaction, because exothermic reactions release heat. But you don't really have to memorize this. You can just think of an increase in temperature as an increase in heat. So if you see any type of temperature change, put heat into your reaction, like I was just saying. If it's endothermic, put heat on the left, exothermic, put heat on the right, and then you can just treat it as any concentration change. Just if you see temperature, you would just look at the heat value in your equation. So for instance, let's say you had this reaction, and I'm telling you that the stress is that there's a higher temperature. The temperature has been raised. So if I see that delta H is negative, that's an exothermic reaction. So let's actually put heat into my equation. So I can rewrite this as plus heat on the right-hand side. Now, when I think of an increase in temperature, I would just say I have more heat. So I can use those same rules. More goes away, less toward. Mult. More away, less toward, right? So, and if I didn't want to put the word heat, I could also put 890.4 kilojoules on the right-hand side, because that's the actual amount of heat that is released. So now we can do temperature changes the same way we did concentration. If temperature goes up, shifts away, more away, less toward. Temperature goes down, reaction shifts toward the side with heat, more away, less toward. So if I have a higher temperature, I would think of that as being more heat. If I have more heat, the reaction shifts away from it. The reaction would shift to the left in order to reestablish equilibrium. If it shifts to the left, what's going to happen to the reactants? They're going to be made. They're going to go up. What's going to happen to the products? They are going to be used up, so they go down. And if heat is now being used up, that would eventually bring the temperature back down. So it makes sense. This is counteracting the stress. So I'm really just treating heat as a reactant or a product. Okay, the opposite, if I have a lower temperature or less heat, okay, here again, here is heat. Heat goes down, the reaction shifts toward it, more away, less towards. So the reactants would be going down over time. I'm using them up. The products would go up over time. And so would now heat be going slowly back up to counteract that stress of it initially being decreased. Okay, take a moment, try this example, check your work. Here's delta H, it's negative, so it's exothermic. Let's put heat on the right-hand side, and now we can treat temperature as any changes in heat. If I raise temperature, more heat, okay, goes away from that side, so it shifts to the left, and I'd be pointing to H2, so that would go up. It's being made over time. If I lower the temperature, this would shift to the right to fill back up the heat, makes sense, and H2 would be going down since I'm pointing away from it. Okay. The last kind of stress are pressure volume changes, and this is only going to affect a gas. gas reactions only. So if you think of increasing pressure, if you remember the ideal gas law, PV equals nRT, increasing the pressure is the same thing as a decrease in volume. So sometimes questions might say increase in pressure, sometimes they might say decrease in volume, and it's the same stress. So if I'm decreasing the volume that I have for these gases to exist, okay, in order to kind of reestablish equilibrium, the reaction's going to shift toward fewer gas moles. I have less volume for these gases, right? So in order to essentially decrease the concentration, I need to shift to the way of fewer gas molecules, right? Because if I all of a sudden lower the volume, then the partial pressures of these things are going to be shooting up because they, and the concentration is going to be going up because I'd have more moles per unit volume now because the volume has decreased. So I need to restore those equilibrium concentrations by shifting to the fewer gas moles. So if you decrease the volume, you have less space for the gases, you're going to shift to the side of the reaction that creates less gases. Okay? So let's say I had this reaction, and I'm telling you the stress is that I have more pressure or less volume. Same thing because they're inversely proportional. So what I would do is I would count the number of gases. So I have 2 gases on the left-hand side, and I have 3 H2s and 1 CO, so I have 4 gas molecules on the right-hand side. So you would be looking at the coefficients and counting them up for all gases. If you have a solid or a liquid or aqueous, do not count it. And if you have no gases in your reaction, you'd have 0 and 0 on each side. Okay, but you would count the number of gases. So if I have more pressure or less volume, right, I have less volume, I have less room for these gas molecules, I'm going to shift to the side that produces less moles. So this would shift to the left. So I'm not using mult for this situation, more away, less toward. For pressure volume, I am going based on the number of gases. If I have more, or if I have less volume, I need to shift to less gases. If I have more volume made, then I can shift to the side with more gases. If I shift to the left, that would increase, I'm pointing to these reactants, that would increase those concentrations over time, and it would decrease the products over time. So essentially I'm changing the number of gases. I'm changing that to restore the pressure over time. Okay, if I decrease pressure, which would be the same as an increase in volume, then the reaction can shift toward more gas moles to reduce the stress. So same reaction, same number of moles on each side, but let's say it's less pressure. Now I would shift to the right. I would be creating the H2 and CO, so they would go up over time, and I'd be using up the CH4 and H2O, so they'd be going down over time. And it makes sense. If I have decreased the pressure, I need to create more moles of gas to fill that pressure back up. Okay, couple of things here. Note that you're only counting gases for pressure volume changes. So for instance, if I looked at this reaction, CO2 gas goes to CO2 aqueous. Predict which way this would shift if I were to increase the pressure. So this has 1 gas on the left and 0 gases on the right. This is an aqueous. So if I increase the pressure, which would be the same as decreasing the volume, I want to shift to the side that has fewer gases. So I'd be shifting to the right. And what would happen to CO2 gas? It would go down. What would happen to CO2 aqueous? It would go up. This actually makes sense as to why gases are more soluble in liquids as you increase the pressure. So like even your soda, why you have the cap on, why it's pressurized, is you want to put most of that gas as aqueous form. You would want to increase the pressure so the solubility of it increases. So this explains why gases are more soluble at high pressure. If you think about what you hear when you open that, open your soda, you hear a psst sound, right? Because that's a lot of times the gas escaping because it's no longer, you've released the pressure and it's turning now from aqueous back to gas. If you have the same number of gas molecules on either side of your reaction, then pressure volume changes have absolutely no effect. So whether you have 1 gas and 1 gas, or 0 gases and 0 gases, then changing the pressure or volume would not shift equilibrium and it would have no effect on the concentrations. Okay, let's just talk about the reason why, going back to the equilibrium constant expression. So here's that same reaction example that I gave before. Let's write the Kp expression. So it's the products over the reactants raised to the power that is the coefficient. Kp, we'll put partial pressures in. And let's derive something further. If you remember from our ideal gas law chapter, Dalton's law was that the partial pressure of a substance is equal to the mole fraction of that substance times the total pressure. So I'm going to plug in this equation for all these partial pressures. Okay, so here's the partial pressure of C, abbreviated with or subbed in with that equation. And now I'm going to cancel out any pressures. Okay, so one of these will cancel out with this one, and one of these squared will cancel out with that one. And I'll be left with a pressure in my denominator. So what does this mean now? Now pressure is affecting my equilibrium constant expression. It's actually in there. So if pressure were to go up, okay, in order for Kp to be constant, because remember this entire fraction essentially has to be constant if I don't change the temperature to be at equilibrium, then to counteract this stress, what would XA and XB would have to do? They would have to go down. So the mole fractions of those would have to go down. So in order for the mole fractions to go down, I'd have to shift away from that side. And the mole fractions of C and D should go up. Well, how would that happen if I shift toward that side? So that's why it's shifting to the side, to the right. And if you notice in this situation, shifting to the right is the side with less moles. This has 3 moles of gases. This has 2 moles of gases. What about a reaction with no change in moles? So here's my Kp expression for this reaction. Notice there's 2 moles of gas on the left, 2 moles of gas on the right. If I were to plug in with the mole fraction equation, you're going to notice that all the pressures cancel out. So if you have the same number of gases on either side, pressure drops out of your equilibrium expression. So it doesn't matter if you've changed the total pressure, it would have no effect on my equilibrium expression because it's not there. So that's why changing the pressure doesn't affect anything if you have the same number of gases on either side, but it does affect something. It does affect it if you don't have the same number of gases on either side, because the total pressure will not drop out. Okay, so note, inert gas note. Sometimes they might mention that the pressure is increased by adding an inert gas. So that's not changing the pressure by changing the volume. That's changing the pressure just by adding something that's not involved in the reaction. And if that's the case, there's no shift in equilibrium. Why? Because the inert gas would not be in the equilibrium expression, and your ratio of the partial pressures will still be the same. So if I look at this example, increase in pressure by adding E. Okay, E is not in my equation. It is not in my equilibrium expression. So the partial pressures of all the other things are still the same. I've just added, I still have the same number of moles, and I still have of each thing, and I still have the same volume, and I still have the same temperature. So by PV and RT, the pressures of those things are not changing. So, right, if the partial pressure of A is the moles of A times R times T over V, those things are not changing just by adding an inert gas. So there would be no shift in the reaction. Okay, so not changing any of those variables, all partial pressures stay the same. So if you see the pressure change because an inert is added, something not in the reaction, that does not shift anything. Take a moment, try this example, and then check your work. So here's the same reaction we've been looking at. There are 1 plus 3, there are 4 moles of gases on the left, and there are 2 moles of gases on the right. So if I were to increase pressure, the reaction's going to shift to the right. I'd have less volume available, so it would shift to the less moles. If I shift to the right, I'm shifting away from H2, so it goes down. If I were to decrease the pressure, okay, that would mean I can shift to the side with more moles and shift to the left, and I'm pointing to H2, so it would go up.